Good afternoon and welcome to this edition of Live from NOIRLab. I'm your host, Rob Sparks, with our moderator, Jamika Marshall. Our guest today is Dr. Dan Lee of NOIRLab here in Tucson. Dan is going to talk about a topic I really enjoy, different families in the main asteroid belt. Remember, if you have any questions or comments, you can enter them in the chat and Jamika will relay them to our guest, Dan. First, I'd like to tell you a little bit about Kitt Peak National Observatory, our facility here in Tucson. Kitt Peak National Observatory was founded in 1958 and is located about 55 miles southwest of Tucson, and this is a NOIRLab facility. It is located on land leased from the Tohono O'odham Nation, and we are indebted to them for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes and 2 radio telescopes as well. And we always do a short news item. Today I'd like to talk a little bit about a recent program called Viaje al Universo, or Journey Through the Universe. I apologize to Spanish speakers who are already criticizing my Spanish pronunciation. Journey Through the Universe, or Voyage to the Universe, is a program spearheaded by Cerro Tololo Inter-American Observatory and Gemini Observatory in Chile. It's a week-long program that happened October 19th to the 23rd, I believe it was. October 19th was the Monday, whatever that Friday was the last day. And each day they'd have a series of astronomy talks, award ceremonies, teacher workshops, and things of that nature online. It was all virtual this year, normally it would be done in person. And at night we did a virtual star party. And we took advantage of the time difference as well. Chile is 4 hours ahead of us here in Tucson, so I was able to do live streams of solar observations from Tucson to our audience in Chile while they were waiting for it to get dark so they could observe the moon, Mars, Jupiter, and Saturn and various objects at night. And this is a screenshot of one of the days when we were doing solar observing during Viaje. It was a lucky shot. This is a hydrogen alpha view, and we actually were lucky enough to catch an A-10 jet flying across the sun. I was not fast enough to snap a picture of it with my camera, unfortunately, but we did have the live stream that was on YouTube Live that we could go back and do a screen grab of. So we do have this moment preserved of seeing that wonderful shot of the plane flying across the sun, which is rare and kind of a special treat. So without any further ado, I'd like to introduce our guest today. Dan Lee is an assistant scientist here at NOIRLab. He earned his BE at, I hope I pronounce this somewhat close correctly, Tsinghua University in China in 2003, and his PhD from the University of Florida in 2013. Go Gators. He had postdoc positions at the University of Florida and the University of Pennsylvania before joining NOIRLab in 2018. Now I will stop sharing my screen and bring Dan on so he can do his presentation. So Dan, you can turn on your video and audio at this point and start sharing your screen.
Okay, let me start sharing my screen. Hopefully there's no technical issues.
Looks good here.
Okay. First of all, thank you very much for the introduction, and also sorry about the confusion because I would like to use a slightly different title for my presentation today, and the new title is "New Insight on the Formation of the Main Asteroid Belt," which I think is a slightly more accurate description of what I'm going to talk about today. So. The picture on the left is just to show you where the main asteroid belt is. And all those white dots, those are asteroids in the main belt in our solar system. You can see they are distributed between the orbit of Mars and Jupiter. And you can see the main belt is not the only population of asteroids in our solar system. There are other smaller populations like Trojans, Greeks, and also there are near-Earth asteroids which are not shown in this picture. But anyway, as suggested by the name, the main belt is the largest group of asteroids in our solar system. And now, because I'm not very good at photo editing, I would like you to use your imagination to draw a picture in your mind. The picture will be similar to this one, but with all asteroids removed. So what you can see. What I see is that the region within the orbit of Mars is very crowded, but there seems to be a very large empty space between the orbit of Mars and the orbit of Jupiter. And actually, this is exactly what Kepler noticed about 400 years ago. He pointed out that there seemed to be a too large gap between Mars and Jupiter. There should be a planet in between. And this idea of a missing planet was strengthened by the so-called Titius Bode law in the 18th century. So this law is a very simple mathematical equation that successfully predict or reproduced the correct orbital radius of all known planets around that time. It also suggests that there should be a missing planet between Mars and Jupiter. And indeed, such an object was later discovered by an Italian astronomer in the first year of 19th century. And that was Ceres, which is also the largest asteroid. And it turns out that this is not the end of the story, it's only the beginning. In the following about 45 years, 4 more asteroids were discovered, and another 1,000 in the following 70 years. And this boost, thanks to the invention of astrophotography, so that astronomers didn't have to look for new asteroids with their naked eyes, they can just take photos. And now the total number of asteroids in the main belt has go over 500,000, and most of them were discovered over the past 20 years, and thanks to the invention of CCD imaging and a lot of new technologies. Asteroids are mostly very small objects. And here you can see Vesta and Ceres. Those are among the largest asteroids we know. But even for those two, they are much smaller than Pluto, which is the smallest used to be planet. So as a consequence, the total mass of the asteroid belt is very small. The total mass of the entire main belt is less than a small fraction of the Earth's mass. So those asteroids are very small objects. However, you need to be careful when an astronomer tells you something is small or is young or nearby, because maybe they are not that small by normal standards. Here is a picture, well, not picture, illustration of the asteroid Bennu, which is a near-Earth asteroid just visited by a spacecraft. And Bennu is the diameter of Bennu is 500 meters. It's a great threat to Earth because it's a near-Earth asteroid. But if you put Bennu in the main belt, it will pretty much among the smallest asteroids that have been captured by existing surveys. There are millions of asteroids bigger than Bennu in the main belt. So the formation of the asteroid belt is, of course, a part of the formation history of the entire solar system. And in the current standard theory or a simplified theory of the formation of the solar system, the formation of the solar system begins with the collapse of a molecular cloud. Let me see if I can put my pointer on. So when the material inside a molecular cloud began to collapse because due to a physical law called the conservation of the angular momentum, the materials cannot reach the central part directly. Instead, they form a rotating structure called the protoplanetary disk. So all planets are formed inside this protoplanetary disk. Eventually, most material, maybe 99% of the material, will reach the central part and becoming part of the sun. There's a small amount of leftover material in the protoplanetary disk that giving birth to all planets, including all asteroids in the main belt. There were actually enough material in the asteroid belt to form a real planet. However, due to the very strong gravitational perturbation from Jupiter, which is with a giant planet somehow formed faster than the rest of the planetary system, due to the perturbation from Jupiter, those materials in the asteroid belt failed to grow into a real planet. And also, over the subsequent billions of years of evolution, the asteroid belt lost 99.9% of its mass. And that's why the total mass of the asteroid belt is so small nowadays. I want to point out that nowadays the asteroid belt is still an active system. There are still collisions between bodies, although very rare. And there are still asteroids escaping from the asteroid belt. And some of them will eventually become near-Earth asteroids or even meteors or meteorites. So let's take a close look at the asteroid belt. Here is a figure shows you the distribution of main belt asteroid in the parameter space of orbital inclination and the semi-major axis. So the orbital inclination is basically how the orbital plane of an asteroid is tilted with respect to the mean orbital plane of the planet. And here we can see the asteroid is not uniformly distributed between the orbit of Mars and the orbit of Jupiter. It has a well-defined inner boundary and outer boundary. And there are also many gaps. So the inner boundary and the outer boundary are actually defined by two orbital resonance. The nu-6, which is orbital resonance with Saturn. And this line is a 2-to-1 mean motion resonance with Jupiter. So orbital resonance is something that occurs when the orbital period of an asteroid and the orbital period of a major planet, such as Mars or Jupiter, are related by a ratio of two small integers. And orbital resonance can greatly enhance the interactions, the gravitational interactions between two objects. And normally for an asteroid, this means the orbit of the asteroid will become very unstable. If an asteroid is, the orbit of an asteroid is falling in a orbit resonance, in a few, it will be ejected from the system fairly quickly. By fairly quickly, I mean in a few million years, which is a very short time scale compared to the entire, compared to the age of the solar system. And not only the inner boundary and outer boundary are defined by the orbital resonance, all those gaps are also consequences of orbital resonance. Because the orbit are not stable, and that's why you cannot see any asteroid in those gaps. And I don't label all of the orbital resonance, but only the 3-to-1 orbital resonance here, because this resonance, this is a 3-to-1 mean motion resonance with Jupiter. It defines the outer boundary of the inner part of the main belt. So the inner main belt, which is bounded by nu-6 and the 3-to-1 mean motion resonance, will be the sort of the central, the focus of our current study of the main belt, and I will explain why. Well, beside those gaps and orbital resonance, another important feature you can see in this figure is those high concentration of asteroid, and those are asteroid families. So an asteroid family is created by catastrophic collisions between big bodies in the asteroid belt. So when such a collision happens and created a lot of small bodies, small asteroid, and over time, those small asteroids will be, spreading over the orbit. And after so many years, those asteroids will be so dispersed in the orbit. However, we can still see them tightly grouping together in the parameter space, and that's why we can still see them in a plot like this. And that's also how we can find and define those families. And asteroid families are very important because they can tell us a lot about the dynamic evolution of the asteroid belt. Nowadays, it is believed that about 1/4 of all main belt asteroids belongs to known families. And about 3/4 of all known families do not belong to any family. We call them background or non-family asteroids. And this picture is, I found it from Wikipedia. So this is a sort of general agreement in the field. But I want you to remember this figure because our study, in a few slides, you will see that we find something that will change this picture dramatically. So like I said, we want to focus on in our study. Oh, by the way, I think I have talked about enough background. So what we are doing recently. So I and my colleagues, we are trying to figure out how, at which rate or how fast those asteroids are being removed from the main belt through those orbital resonances. And now we want to focus on the inner main belt because the inner main belt, this region, has a few very good properties. So this is a zoom in plot of the inner main belt. You can see it's bounded by the nu-6 resonance and the 3-to-1 mean-motion resonance. And if you look at the distribution of asteroids, you can see there seems to be a very uniform background made up by non-family asteroids. And upon that, you have only a few major families. So the overall composition of this region is very simple. It's easy to separate family asteroid from the background asteroid, which is very important because when you want to study the dynamics of the asteroid, you want to treat family and non-family asteroids separately because they are experiencing sort of different dynamic evolution. Their initial conditions are also different. And that's why we want to focus on this part. And for our study, at first, we want to compare the properties of non-family and family asteroids like this. And here we found something quite unusual. So this plot is a histogram of the size of asteroid. So basically, it tells you how many asteroids for a given size of asteroid. Here, the x-axis is absolute magnitude or brightness of an asteroid, and we know it indicates the size of an asteroid. So the y-axis is how many asteroids in logarithm. And those color figures in green, red, blue, and cyan are the histogram of those family asteroids you just saw in the previous slide. Oh, by the way, because this histogram shows you how, go ahead.
Sorry. Didn't mean to jump in. I wanted to first say that we have some questions and comments already for you and for Rob in the chat, but also wanted to make sure you could see our video, just a reminder to make sure you could see our videos for the transition. Okay. So in the chat right now, we have several questions. First, I'd like to welcome everyone who is in our YouTube chat today. We are pleased that you're with us talking about the new insights on the formation of the asteroid belt with our guest scientist today, Dan Lee. So Dan, we have our first question from Liz Flemings, who is with us from Memphis, Tennessee. And Liz asks, how does the main asteroid belt affect our solar system?
Okay, I think let me share my video. I would like to talk with my face on screen. So this is a great question. The asteroid belt is as we mentioned, the total mass is very small. So it's hard to say the effect of the asteroid belt on the solar system. But there indeed that the asteroid belt has an impact on the Earth. As I mentioned, the asteroid belt is an active system. It's still sending asteroids to the rest part of the solar system. Many of them will, well, not many of them, but a certain number of them will eventually become near-Earth asteroids. So I don't know when that will happen. I mean, a major impact from something from the main belt on Earth, but in theory, it can happen. So I think that's maybe one example how the main belt can impact, well, not the solar system, but our lives.
Oh, that's a fantastic answer, Dan. I didn't realize that so many of our near-Earth objects come from the main asteroid belt.
Well, yeah, that's actually one of the reasons why we're going to study the dynamics, the asteroid belt dynamics.
Excellent. Okay, let's go to the next question. Thank you so much for that fabulous answer, Dan. Liz, I hope that was that answered your question. And if not, go ahead and send us a follow-up in the chat. Okay, so we have Susana Acevedo commenting from Chile, and she says, "Hello, Rob. Greetings from Chile." And she says, "There's a beautiful night in the city of La Serena to see the stars." Thank you so much for joining us, Susanna. And Susanna also has a question. She says, "Dan, I want to know, how long can an asteroid belt exist?"
Well, the asteroid belt has been existing for more than 4 billion years. It's as old as a solar system. And I cannot see any reason that it will disappear soon. And of course, there are small asteroids leaving the asteroid belt, but the total number is still very small compared to the total number of asteroids. So I think the asteroid belt will basically exist forever, as long as, you know, the solar system is still there.
Okay. Susan, hopefully that was a good answer to your question. Thank you, Dan. And also, Dan, Liz from Memphis has a follow-up question, and I know that you answered this just a little bit ago, but I think she just joined us.
No
the
problem.
question was, we appreciate it. The question was, what are the different colors here on the current chart that you have up? What do those different colors mean again?
Okay, so those curves are the size distribution of asteroids, and the different colors corresponding to different families. Maybe I should move a little bit back. Oh, can I do that? Yeah, here. And you can see this figure shows a few major families in the inner main belt: Vesta, Flora, and another large family, which is basically a combination of 3 small families. And let me see if I can move forward. And those color curves, the green, the red, and the blue one, are corresponding to the 3 major families. And we have a new family, Massalia, which is a very small family, didn't show up in the previous slide. And the other 2 curves, the orange and the black curve, I will talk about them in detail momentarily.
Thank you so much, Dan. Liz, hopefully that answered your question. Dan, awesome. Thank you. We have some more questions, but I will come back in a little bit to ask them for you. Thank you so much. Please continue with the asteroid belt.
Okay. So I mentioned that we found something quite unusual in this plot. Specifically, if you, I would like to draw your attention to the black curve. So the black curve is the size distribution of all non-family, all background asteroid. And the orange curve just below it is the size frequency distribution of all families combined. So this may looks normal to you, but you can see there's a striking similarity between the 2 curves. And actually, there's no good theoretical reason for that similarity. The non-family and family asteroid, they are experiencing different dynamic evolution histories. So their size distribution should be quite different, but we see they are almost the same. And we want to find a reason for this. One apparent reason is that maybe the definition of the family or non-family asteroid is not that accurate. There are interloopers between those, inside those 2 loops. So indeed, if we come back to this figure, you can see we have 3 major families, and there seems to be a very high concentration of non-family asteroids just around those major families. And we call those guys the family halos. So apparently, the previous algorithms that was used to define the families failed to include those halo families into the families. So, but the question is by how much? And we want to figure out how many family halo asteroids in this figure. And we want to find a better way to define the family halos so that we can sort of minimize the difference between the properties of all family asteroid as a whole and all family halo asteroid as a whole. Well, and meanwhile, we want to maximize the difference between the overall properties of all non-family asteroid and the family asteroid. Okay, I know it sounds confusing, but the figure here shows you what we have done. So basically, we have found a new way to define all those halo asteroids, those very near to the families, so that we can see the overall property of the halo and all family asteroids are very similar to each other. And both of them are quite different from the non-family, non-halo asteroid as a whole. So based on comparisons like this, we reach a conclusion. Oh, well, just to remind you, previously we believe 1/4 of all inner Maybelt asteroids belong to families, but now we think that that conclusion should be changed. We find that the family and family halos combined makes up about 85% of all non-family. I'm sorry, 85% of non-inner Maybelt asteroids. There are only a very small portion, 15% of non-asteroid are truly non-family background asteroids. So this is quite different from the general agreement nowadays. And so this is kind of deviation from our initial goal of this study. We want to study how asteroids are leaving the asteroid belt. For that purpose, due to some theoretical reasons, we want to focus on the non-family asteroid. But now we know there are actually much fewer non-family asteroids than we thought. Anyway, now I think we are ready for to move on to focus on the non-family asteroid. And we want to focus on those high inclination region because this region seems to include no family or family halo asteroid. They seem to be pure non-family asteroid, which is good for us. However, we still want to double check their properties before moving on. And that's why we found another thing quite unusual. So in general, if those are truly non-family asteroids, we expected that those asteroids are well mixed together, which means if you define several subgroups of asteroids within this population of non-family asteroids, you should not see any difference between those subgroups. However, this is not what we saw. The figures on the right shows you that we define two subgroups based on the surface albedo of those asteroids. One group is called CC, one group is called NC, which stands for carbonaceous and non-carbonaceous asteroid, respectively. You don't have to know exactly what they are, but keep in mind, if those non-family asteroids are truly non-family background asteroids, we are expecting to see no difference at all between those two subpopulations. But we see clearly they are different in the distribution of the eccentricity or in the distribution of the inclination. Well, there might be a theoretical explanations for this, but for us, I think the most straightforward or the easiest explanation for this difference is that those CC and NC asteroids are also not true non-family asteroids, but sort of family asteroids. They are also sort of produced by the catastrophic collisions that create families. And so the conclusion is, even for the 15% of asteroid families, we believe that they are not truly non-family asteroids either. Those non-family asteroids are actually remnant of, we call it ghost families. So the difference between those ghost families and the major families we saw earlier is that those ghost families are very old. They may as old as the solar system itself. And because they are very old families, the orbital parameters are no longer tightly grouped together in the parameter space. They are so dispersed in the parameter space, and that's why it's hard to find them using traditional method. But still, there are some clues, like the one I just showed you in the previous slide, their existence. So if we combine those two new conclusions we found, family and the family halos are 85% of all asteroids. The rest, the remaining 15% are actually remnant of ghost families. And then we can reach a quite new conclusion that the origin of all asteroids in the inner May belt can be traced back to only a few large bodies. And this conclusion supports the model that all asteroids formed big through gravitational collapse of the material in a protoplanetary disk. And I want to point out that we are very glad because we reached a conclusion quite different from the general agreement, but still there are some theoretical questions very hard to explain if our conclusions are right. For example, at least this is not consistent with the current understanding of the early evolution history of the solar system, because we know Jupiter can form very quickly, and a very strong gravitational perturbation from Jupiter cannot be ignored. Under that condition, how you can form such only a few big bodies is still a question. And also, if there were only a very few large bodies in the asteroid belt at the very beginning, that means the mutual collision between them will become very rare. And we know there are so many small asteroids in the belt, which means the mutual collisions happen very frequently in the early times. When you have only such a few large bodies, you need to find a way to explain why the mutual collision still happened. So anyway, nevertheless, those are the conclusions based on our current studies. And okay, until this moment, we're still deviating from our original path. Recall that our original goal of the study is to study how fast, at which rate the asteroids are moving out of the asteroid belt. So let's come back to this topic. So there are a few physical mechanics that can remove asteroids from the main belt. We believe the most important one of them is called the YARKOVSKY effect. So this effect was first studied by not an astronomer, but a civil engineer who worked in a railway company. His name is Ivan YARKOVSKY. So this effect can be explained by the figure on the left. So when you have an asteroid, it's being heated by the sun. The solar radiation is coming this way. So we can imagine that one side of the asteroid is warmer than the other side. However, the hottest point on the surface of the asteroid is not a point directly pointing to the sun, but sort of offset. I think this is consistent with our daily experience because we know the highest temperature of a day never occurs at noon, but sometime around 2 p.m. or 3 p.m. So this is exactly what happened at the surface of an asteroid. So because the hottest point is not pointing to the sun, so the maximum re-emission is not pointing to the sun. And the net effect of that is the asteroid will feel a net force along the direction of the orbital motion. So it will feel a force pointing pushing it forward or backward, depending on its spin direction. And over time, this force will also push the asteroid outward or inward inside the solar system. And this is a very weak effect. It's pretty much like powering your car with a flashlight. So it's a very weak force. But remember that time is the most plentiful resource in the universe. So given enough time, this effect will produce very considerable effect on the orbit of an asteroid. So we want to focus, we want to study, we want to measure this effect, and we want to focus on the inner May belt because, again, there are a few very good reasons why the Yarkovsky effect can be measured using the observations on the inner May belt. Imagine that you have an asteroid. Under the influence of the Yarkovsky effect, it will move inward or outward. When it reaches one of the orbital resonance, nu 6 or the 3-to-1 mid-motion resonance, it can escape from the inner May belt. And the Yarkovsky effect can be described by a relatively simple equation. I'm sorry, I have to include just one equation in my presentation. So this equation describes how fast the orbital radius of an asteroid is changing under the influence of the Yarkovsky effect. Notice that there is a capital D in this equation, which is the diameter of the asteroid, which means the Yarkovsky effect depends on the size of the asteroid. Basically, smaller asteroid moves faster. So given for a given population of asteroid, over time, you will see fewer and fewer smaller asteroids. So the size frequency distribution will evolve with time, which is something can be tested. You can compare a model with the observations of a certain sample of asteroid. However, there's a weak point in this method because there's an ambiguity. When you see there's a lack of small asteroid, you don't know whether it's caused by the observational bias because smaller asteroids are difficult to observe. So you may miss some of them in your survey. So it's kind of difficult to tell that from the effect caused by the real physical Yarkovsky effect. And that's why the inner May belt, this region is important for us because it has another very good property. Notice that the escaping route of an asteroid, the length of the escaping route depends on the inclination. For a high inclination asteroid, the escaping route is short. And for a low inclination asteroid, its escaping route is longer, which means a high inclination asteroid is easy to escape from the inner May belt and driven by the Yarkovsky effect. So this gave us another thing we can test against the observations, which is the mean inclination of this population of asteroids. And this is exactly what we did in our study. We developed a model of asteroid. We can calculate over time how the size frequency distribution is evolving with time and how the mean inclination is evolving with time. So the blue curve is the output of our model, and the black dot are the observations. And here you can see our model is very successful in reproducing the observations. And from here, we can estimate the time scale of the Yarkovsky effect, which is this number in this equation, which is another very important number in this equation. Is basically tells you the characteristic time scale of this physical effect. So this is basically where we are right now. And we are still looking for new data that we can do a better job in the modeling and the comparison and the estimation of the Yarkovsky effect. And specifically, we look forward to the start of a new survey called LSST, the Legacy Survey of Space-Time, which will be carried out at the Rubin Observatory, which is also part of the NOIRLab. So this new facility combines a very large telescope, 8.4 meter telescope, and a very wide field camera, which has more than 3 billion pixels. Traditionally, it's very difficult to combine large aperture and large field of view, but for LST, we are able to do this, and it will give us a super high survey efficiency that has never been achieved before. And of course, the new data will be be useful for many aspects, but for us, the LSST will almost increase the known number of asteroids by an order of magnitude over about 8 or 9 years. And this will become super useful for us, because recall that we have to deal with the ambiguity between the observational bias and the models and physical models. So the new data from LSST will definitely be very, very helpful to us. So I think that's the end of my talk. I hope you enjoyed. I hope my talk helped you take a break from the politics. So thank you very much.
Thank you so much, Dan.
Thank you, Dan.
Okay, so in the chat, Dan, I have put your paper. This paper is your most recent one. Oh, I have a little one here, which this is Theo, so you may hear him, it's fine. So their paper, A New Observational Constraint on the Yarkovsky-Driven Mobility of Main Asteroids. So I dropped a link in the chat. So for those of us trying to follow along with what you were saying, specifically about the Yarkovsky effect on the asteroid belt, where would you direct us to look? The first couple of pages to get an idea of more details on the impact of this radiation effect?
Yes, exactly. I think the introduction contains most useful background knowledges, and so you can get a very good idea with, of course, with more details about the effect and how we can test it, how we can measure it.
Okay, thank you. And so that is in the chat for those of you who in our YouTube audience. If you have a chance to get to that link and you have questions in the next 15 minutes before we wrap up for our science guest, Dan Lee, today, please leave those questions and comments in the chat for us. Dan, I do have a few follow-up questions myself. We're talking about the asteroid families and the three in particular here in the main asteroid belt. What are the characteristics of each of those families, physical characteristics that that each of those three families have, and are they really that different physically if we were actually just to look at them?
Well, first of all, each family, those families, they have different origins. Each family was created by a single collisional event, a major collisional event. And also, I don't know if you remember those families. Let me move back a little bit. Each family has a name, of course, and actually named by the largest member in that family. For example, the family Flora is named after the asteroid Flora, which is the largest member of that family. And it is, I don't know if it's true for all families, but at least for several of them, that the collision was actually between a smaller body and a bigger body. For example, in the case of Flora, maybe the collision was between a small asteroid and Flora at the very beginning. And then after the collision, a lot of small asteroids were produced. And also there were mutual collisions between those smaller asteroids during the evolution. So anyway, it's end up with a very big family nowadays, contains thousands of family members in this family. So.
Okay, no, thank you for clarifying that, Dan. And so as we are looking forward to the new capabilities that the Vera C. Rubin Observatory will bring with LSST, can you give us maybe one just particular thing, specific thing that LSST should be able to do to give us more insights into this new formation theories on the asteroid belt, where they came from. How can LSST help us with that?
Let me show you the science frequency distribution and our models again. Can you see my cursor? Somehow I lost it. Okay.
Yes, we can see it.
Okay, it's back. So I mentioned that the black dot are observations. Basically, we want to compare our model with observations. But also note, those are gray points. Those gray points are also observations, but we believe those data are not observationally complete because current surveys do not provide enough survey sensitivity. And imagine that after the new LSST data is available, all those gray points will become solid black points, which means we can compare our model with observations at a much wider range of magnitude. Currently, this part is not taken into, although we reproduce this trend very well, but we know it's not real trend, it's observational bias. This is one example how the new data from LST will be helpful to us. And of course, all those gray points here and will become more trustable. And we have many more comparisons between the model and data that I don't show in here, but all of them will be benefit from the new data from LST. That's why I was so looking forward to them.
Absolutely. And so this data, once the data starts coming in, will this data be available to the public, especially, I'm sure after a little while, but especially after earlier you were just informing us that quite a few of the near Earth objects come from the asteroid belt. And so is that, how does that data go from, say, LSST and your data to the near Earth objects office that works on that?
Yes, actually that's our sort of ultimate goal, is to estimate at which rate those asteroids are reaching our neighborhood.
Okay.
So now we are still in the first step, which is to figure out at which rate they are leaving their hometown. And you can imagine there are still a few intermediate steps. Not all of them will reach Earth, which is good news for us. But yeah, yes, the ultimate goal is to figure out at which rate, because as we mentioned before, they pose a threat to us, right? Those near Earth asteroids. That's why we want to monitor, not only observe and monitor them, but to figure out theoretically where they are coming from and which rate they are coming toward us. Yeah. Yeah.
Just a quick follow-up on that. Do you work, or you and your team work with the, so there's the Center for Near Earth Object Studies, the Jet Propulsion Lab. Do y'all collaborate with them?
I'm not working in that project, but I do have collaborators which has a working relation with that center. And yeah, I'm personally not a part of that. My major job is I'm a scientist at NOIRLab. So the most important part of my job is to work for the 3.5 meter telescope, the WIN telescope on Kitt Peak. So, but yeah, I hope that answered your question.
It did. Thank you. Thank you so much, Dan. And I will continue monitoring the chat for more questions and comments on new insights on the formation of the asteroid belt. Over to you, Rob.
Okay, thank you very much, Jamika. That was very interesting. I also just got to say that I love the concept of ghost family, since we just had Halloween. So that crossed my mind how appropriate that was.
Oh, that is good. I didn't even catch that.
I also have always loved the YARKOVSKY effect, or been fascinated by it, because I understand that the Jamika talked about potentially hazardous near-Earth asteroids. That's one thing that makes predicting their orbits in the future somewhat troublesome sometimes, because that'll affect some asteroids' orbits if we try and project out and just say, well, it's going to miss us in 2050 and 2100, but 2150 we start having difficulty. Of course, how far out depends on the asteroid, but so That does cause some prediction problems.
Yeah, it's also kind of interesting because the Yarkovsky effect was first studied not by an astronomer, by a engineer, and his study was totally ignored by almost 70 or 80 years. And after almost 80 years, people began to realize, okay, this should be a very important effect. It's probably the driving force, a major driving force that's caused those asteroids leaving the asteroid belt. So it's kind of amazing.
And as we get ready to wrap up here, Jamika, I believe next week is live from NOIRLab at Gemini, correct?
Yes, thank you so much for that, Rob. Next week is live from NOIRLab here at Hawaii, and we will have two fantastic science guests for you next week, talking about collaboration among the observatories here on Mauna Kea.
Okay, great. Well, that's wonderful. So I'd like to thank you, Jamika, for being our moderator. And
thank you,
Jamika, for your presentation. That was very interesting.
Thank you, Robert.
And we hope to see you next week on Live from NOIRLab. So